Please welcome on the stage Aliaksandr Valialkin. He's a co-founder and CTO of a sexy company called VictoriaMetrics, and he'll tell you about cost-effective observability.
Yeah, thank you. I'll talk you about cost-efficient monitoring in Kubernetes, especially in Kubernetes. Let's meet. I'm Aliaksandr Valialkin, and I also known as Valiala. That's my nickname, which is used in social media. You can find me in Twitter, GitHub, LinkedIn, under this nickname, Valiala. And I like creating useful tools for DevOps, and I like creating these tools in Go, because I believe that Go is the best programming language for creating DevOps tools. And also I hate complexity and over-engineering. That's why I'm trying hard to simplify lives of Kubernetes users, because Kubernetes is sometimes is complex. And as I'm a CTO at VictoriaMetrics, as already was mentioned. So why we need to monitor Kubernetes? Because monitoring observability is a relatively new word and relatively new trend. Before that, nobody cared about observability, and everybody was happy if something went wrong. We could log into the system and discover what happened, whether it's lack of CPU, memory, or some error happened there. So why do we need monitoring in Kubernetes? Because it simplifies many tasks. And simplifies our lives as DevOps. Observability helps you identifying when some resource usage becomes too high in your Kubernetes, and this helps you proactively adding these resources, proactively making capacity planning, such as adding more Kubernetes nodes if there are not enough resources in Kubernetes cluster, or increasing limits on CPU and memory for your pods running in Kubernetes. Also, monitoring helps you attribute costs between different teams. If you run Kubernetes in a large company, it is likely that this Kubernetes is used by many different teams, and many different teams use this Kubernetes differently, and some teams may use a little bit of this Kubernetes, and other teams may run very heavyweight pods there, heavyweight deployments there, and it is good to be able to measure costs, attribute this cost per each such team, and monitoring helps in this case. And there are such projects as OpenCost and KubeCost, which help significantly with this. And these projects are based on observability signals such as metrics. And also monitoring helps figuring out what happened after the incident, because you will have metrics, historical metrics and historical logs, and you can investigate these metrics and logs in order to understand what happened in your system and how to prevent this in the future. That's why monitoring is important in Kubernetes. Which types of monitoring data to collect? I think that the majority of you know these types of data, but let's repeat them. This is metrics. This is events. Events in Kubernetes are usually generated by control plane, when some important events happened, and such events are just structured logs, but many Kubernetes users do not know about these events, but it's very important to collect them and to know that they are generated and to know how to use them when something needs to be troubleshooted in your Kubernetes cluster. The next is logs, obviously, which can be generated by Kubernetes control plane components and also by applications running in Kubernetes. Recently, different observability vendors say that it is good to collect traces as an observability signal. I think that it sounds good, but has some issues. Let's return to these issues later. And the fifth signal for observability is continuous profiling. You already probably attended today's talk about continuous profiling. It's a new hot topic for observability, but I think that it is overrated. I'll talk about it later. What is the typical Kubernetes monitoring at the moment? I think that the majority of you use Prometheus operator for observability in Kubernetes. What does this Prometheus operator do? It collects various metrics from different services. For example, it collects per node resource usage metrics for CPU, memory, disk I/O, network usage, and so on. It collects per container resource usage metrics via C-advisor process, and per node resource usage metrics are collected from node exporter process. It also collects various configuration metrics from Kubernetes objects via kubestate metrics process, and this process usually generates the majority of metrics which are frequently unused. Let's return to this later. And Prometheus operator allows collecting metrics from your applications which you deploy in Kubernetes if you properly annotate these deployments, these pods via Prometheus annotations. And if you use Prometheus operator in your Kubernetes and you run many deployments, many pods in your Kubernetes, then I think that you are familiar with the following problems in this case. The first problem and the biggest problem is high memory usage and disk space usage for Prometheus in this Prometheus operator. Another thing, if this Prometheus hits memory limits, then Kubernetes kills him, this Prometheus, and it restarts. But the problem is that recovery of Prometheus, highly loaded Prometheus, is unreliable and takes a lot of time. It can take literally hours if your Prometheus was highly loaded and was collecting a lot of metrics. This leads to high infrastructure costs because you need to increase memory limits for Prometheus, allocate more memory, allocate more persistent volume space for Prometheus, and this increases infrastructure costs. And also this increases maintenance costs because when Prometheus crashes because of memory limits, then you need a lot of manual work in order to bring to life this crashed Prometheus. And also, when you collect metrics in Kubernetes cluster and then send them outside this cluster to external Prometheus system, then you may hit the problem with high networking costs because egress costs, egress networking is usually paid in major cloud providers, and the costs for this egress networking are quite high. Why Prometheus uses too much memory? Because it collects, in Kubernetes, it collects a lot of metrics, and a big share of these metrics remains unused. You never use them in alerting rules, you never use them in dashboards, you never use them during incident investigations. And this big number of metrics leads to high cardinality issues. That's a common phrase. Whenever you hear this phrase, this means that too many metrics are collected by some systems such as Prometheus. Another problem is that typical observability in Kubernetes, which is performed by Prometheus operator, usually attaches many long labels to every collected metric during the collection of these metrics. It may attach labels which you define per pod. It may attach labels which you define per node, per each metric collected from the given pod and from the given node. So the total number of such labels which are attached per each metric may exceed 40, and the total length of these labels per each metric may exceed kilobytes. And this adds up to memory usage of Prometheus, because Prometheus needs to keep this labels information in memory. And another problem is short-living pods. When you pods in your Kubernetes restart frequently, every new pod generates new set of metrics. Why? Because every new pod has this pod label, which is required, and if this pod is stateless, this pod label is different per each restart of the pod. And this leads to new set of metrics or time series which are stored in Kubernetes, in Prometheus. And this issue has a name. It is named high churn rate. So how to reduce memory usage in Prometheus? The first thing which you must do is to drop unused metrics, obviously. And it is quite easy to do if you know this set of these metrics. It can be done with reliable rules in Prometheus with the action drop in these reliable rules. And from my practice and from practice of Prometheus users and VictoriaMetrics users, the majority of such metrics, unused metrics, which introduce the biggest share of memory usage are histograms, because in Prometheus, a histogram is a set of metrics for different value range buckets, and every histogram generates a set of metrics, and usually this set of metrics contains 10 or 20 or 30 or more metrics, and if you generate a lot of different histograms by your applications, then these histograms add up a lot of new metrics, new time series in Prometheus, and this requires a lot of memory. That's why histograms is the first victim to drop when you explore unused metrics. Another issue with these unused labels, if you notice that some labels which are attached to every metric in every collected metric in Prometheus isn't used, then it is a good idea to just do not attach this label, or if you have no access to the configuration which attaches these labels, then it is a good idea to just drop this label before storing them in Prometheus. And this will reduce memory usage of Prometheus. Another thing which you can do is to reduce the frequency of restarts of your pods. This will reduce this churn rate. And the main source of high churn rate in Prometheus, from my practice, is horizontal pod autoscaling. Because horizontal pod autoscaler may frequently restart these pods, add new pods, remove old pods, and it makes this frequently, and this introduces high churn rate to the metrics and increases memory usage for Prometheus. So the first thing to do is to reduce the frequency of this resizing in your horizontal pod autoscaler if you use it, or just don't use it and manually scale the number of pods according to resource usage metrics. And another thing is that you need to keep an eye on the number of unique values per each label which is attached to every metric. This is named label cardinality, or just cardinality. Why it is important? Because big number of unique values which are attached per each label generate big number of unique time series, and every such new time series needs additional memory for Prometheus. That's why it's important to keep an eye on such labels. And an easy thing which you can do, just increase the scrape interval, the interval for scraping metrics in Prometheus. This will instantly drop your memory usage. And for example, if you increase the scrape interval from 10 seconds to 20 seconds, then it is likely that the memory usage of Prometheus will drop at most twice. So that's a very easy thing to do. And how to detect unused metrics in Prometheus? Anybody have ideas? No. Yeah, it's not simple. And there are two ways. The hard way is to manually inspect all the PromQL queries across alerting and recording rules, across all your dashboards for Grafana, across your runbooks, which you use when incident happens, and then compare this set of metrics which are used in these log-scale queries with the actual set of metrics, collected metrics in Prometheus, and after that, drop unused metrics. That sounds hard, and that's it. And there is an easy way. If you use VictoriaMetrics instead of Prometheus, VictoriaMetrics provides Cardinality Explorer tool, and this Cardinality Explorer tool just shows you unused metrics. Let's look at this example. That's a screenshot of one of the tables shown by Cardinality Explorer. You can see the metric names, and they are sorted by the number of time series per each metric name. The bigger number of time series means usually bigger number of big amounts of used memory. So if you drop metric names from the top of this table, then you will gain more memory usage effect. You will reduce memory usage more. And the second column contains the number of requests for the given metric. Why it is important? If you see 0 in this column for some metric, this instantly means that this metric wasn't requested in any queries from alerting rules or recording rules, from Prometheus, from Grafana dashboards, from anything, since the last restart or since the last reset of these counters. If you see 0 in this column, then just drop this metric, and it will not hurt you, but it will reduce memory usage. And the third column contains the last time when this metric has been requested in some query. And if you see that the metric has been requested last time hours ago or days ago, then it is likely that this metric is not so important, and probably it can be removed or can be optimized somehow. The Cardinality Explorer contains other tables. For example, it contains this table which shows labels which are attached to the biggest number of time series. And if you see labels which you do not use in your queries in this table, that it is likely that these labels can be safely dropped without any problems, but this will reduce memory usage. Another table shows that label value pairs with the highest number of series. This table also can suggest you that some of these label value pairs are not used in your queries, and it may be dropped. And the last table shows the number of unique values per each label. This table may help you identify labels with a big number of unique values, with high cardinality label values. And this also can help you reduce memory usage if you drop such labels or reduce cardinality for such labels during collection of the metrics. So how to reduce memory usage in Kubernetes monitoring? The first thing which I can do is to use vmagent instead of Prometheus for scraping metrics. Why? Because vmagent saves cost. What is vmagent? Vmagent is a collector of metrics which can be used as a drop-in replacement for Prometheus. It understands Prometheus scrape configuration. It can perform service discovery in Kubernetes and in other systems which are supported by Prometheus. It can collect these metrics, and it can then transform these metrics, apply relabeling in the same way as Prometheus. It supports the same relabeling types, and then send these collected metrics to the configured destinations. And you can configure multiple destinations, and you can configure multiple relabeling rules per each destination. So it's very versatile system. And but the main advantage of the system is that it allows you saving a lot of costs, because it uses literally 10 times less memory compared to Prometheus in agent mode. Prometheus in agent mode is a Prometheus which collects metrics and then sends them to some configured destination. It doesn't store them locally. So when compare Prometheus version 3.0, 3.0, it's important to mention, because Prometheus developers say that Prometheus 3 version 3 uses smaller amounts of memory compared to the previous Prometheus versions. And this graph shows that vmagent uses 10 times less memory for the same amounts of metrics for the same configuration in Prometheus in Kubernetes compared to Prometheus. The next graph shows that you may save not only on cost on memory, but cost on network usage. vmagent, when it sends collected metrics to VictoriaMetrics, it automatically switches to more optimized protocol for sending these metrics. And this more optimized protocol uses ZSTD instead of snappy compression library, and this allows saving network costs by up to four times. This is very important if you collect metrics from Kubernetes clusters and send them to external system, external VictoriaMetrics or Prometheus. And also vmagent saves you up to 2 times on CPU costs. You want to make a photo? No? Oh, okay. And when you collect metrics by vmagent, I recommend you sending these metrics to VictoriaMetrics. Obviously you can send them to any Prometheus compatible storage, which supports Prometheus remote write protocol. You can send them to Prometheus, you can send them to Mimir, you can send them to Thanos, for example. But I recommend you send them to VictoriaMetrics because this will automatically save you these networking costs by 4 times because other systems do not support this protocol. And also VictoriaMetrics is more resource efficient compared to Prometheus. It uses up to 5 times less memory for the same amounts of collected metrics. It uses up to 4 times less disk space for the same metrics, up to 2 times less CPU usage. And also VictoriaMetrics is much faster during restarts when you update some configuration or you upgrade version of VictoriaMetrics or your application of Prometheus. It is important to have this low restart times, and Prometheus isn't good in this case if you collect a lot of metrics. And VictoriaMetrics restarts literally 100 times faster than Prometheus. And if VictoriaMetrics crashes because of some reasons, such as out-of-memory crash or kill 9 call or some other crashes, it restarts much quicker compared to Prometheus because VictoriaMetrics doesn't use this write-ahead lock. It uses LSM trees, another data structure for storing data and for ensuring that this data isn't lost after unclean shutdowns. That's why it restarts much quicker compared to Prometheus. So how to reduce costs in Prometheus in Kubernetes? You can manually install this VM agent and set up this VM agent or VictoriaMetrics in Kubernetes, but it is much better to use the already built solutions such as VictoriaMetrics operator for this case, because VictoriaMetrics operator is a drop-in replacement for Prometheus operator. It supports the same or similar CRDs like Prometheus operator. It can migrate CRDs from Prometheus configuration operator to VictoriaMetrics CRDs. And when you install VictoriaMetrics operator instead of Prometheus operator, you instantly save costs on memory, CPU, network, and persistent volumes, as I shown before. And as additional benefit, you can save additional costs by identifying unused metrics and dropping these unused metrics with the help of Cardinality Explorer. Let's look at the logging in Kubernetes. Logging in Kubernetes is needed for collecting logs from running containers and sending them to a centralized storage. And if your Kubernetes contains a lot of such containers, then and these containers generate a lot of logs, then this can be expensive. Let's look at typical systems which are used for collecting these centralized logs in Kubernetes. The first system is Elasticsearch. It has an advantage that it provides fast full-text search over big amounts of logs, but it has disadvantages. The first disadvantage is it is non-trivial to configure with this index lifetime management policies. If you work with Elasticsearch, you probably know about this. And very big problem with Elasticsearch on large-scale logging is it requires a lot of memory. It requires literally terabytes of memory for collecting tens of terabytes of logs, and tens of terabytes of logs is quite small amounts of logs nowadays. Another solution is Grafana Loki, and Grafana Loki solves the main problem of Elasticsearch. It uses much smaller amounts of memory. It requires much smaller amounts of memory than Elasticsearch for these terabytes or petabytes of logs. But Loki has another problems. It has complicated architecture with many moving parts, and every moving part requires non-trivial configuration in YAML, which consists of hundreds of different lines, and these lines usually and options are usually undocumented, and they usually change with every new release and break. So that's not so good. And production grade Loki requires object storage. You can set up Loki for storing data on persistent volume, local disk, but this isn't considered production ready, and production ready Loki requires object storage, and this introduced additional dependency which needs to be managed, needs to be monitored, and needs to be dealt with, configured. Grafana Loki also has very poor support for labels with big number of unique values, such as user ID, trace ID, IP address, and so on. If you try using such labels in Grafana Loki, storing logs with such labels in Grafana Loki, you will instantly notice increased memory usage, and it will stop working. This is my opinion that Grafana Loki has inconvenient query language. This query language is based on PromQL, and PromQL, from my opinion, PromQL is very bad query language for logs. It isn't suited for logs at all, and this query language for Loki looks awkward and inconvenient for users, for typical queries of logs. And another problem that Grafana Loki is slow when you search over big amounts of logs. Why? Because of architecture decisions. It literally scans all the logs, reads all the logs, and scans these logs for the given filter. And if you have terabytes of logs or petabytes of logs, then this may take a lot of time and a lot of resources. And another solution is Victoria Logs for centralized logging.
It's not fair, you forgot the pitfalls.
Oh, okay, that's good. Yeah, that's my fault. Let's talk about ClickHouse after the talk. Okay. Victoria Logs, compared to other solutions, compared to Elasticsearch and Loki, is very easy to configure. It literally runs with zero configurations, and it runs optimally on any hardware without any tuning. You don't need to configure any tables, any database schemes, any index lifetime management. It works out of the box. And it supports fast full text search like Elasticsearch, but it uses a slightly different approach, which requires less memory. And it has query language, which is named LogsQL, which is optimized for typical queries over large volumes of logs. It supports fast filtering over logs, it supports fast analytics over logs, and it supports various useful transformations or parsing of types of these logs during query time. And it supports high cardinality log fields, contrary to Loki. You can safely save logs with trace ID, user ID, and IP, and other log fields with high number of different values. And it scales vertically and horizontally. Vertically, this means that you can increase the capacity of Victoria Logs by increasing memory and CPU limits, or increasing disk space, persistent disk volumes. Or you can scale horizontally if you reach some vertical scalability limits. You can add more nodes into Victoria Logs cluster and get linear scalability. And Victoria Logs is very cost efficient. It requires much smaller amounts of memory, CPU, and storage compared to Elasticsearch and Loki. What about downsides? I don't know. I was thinking hard while preparing this presentation, but couldn't find any disadvantages. Sorry. And let's look at some real use quotes about VictoriaLogs. The first quote is from the user who was running Elasticsearch before that, and after that the user tried VictoriaLogs. And you can read that Elasticsearch required 27 nodes with around 600 CPU cores and around 4.6 terabytes of memory. And this Elasticsearch cluster has been replaced by a single node VictoriaLogs instance with, which runs on 8 CPU cores and 64 gigabytes of memory. And they... Sorry? No. Oh, yeah. The single point failure has a solution. You can run two single node versions of VictoriaLogs and send the same data to these instances and query any of these instances. So the user is very impressed, and you can go to this link and read the conversation with other users. Another quote from the user who migrated from Loki to VictoriaLogs. And this user said that the query time reduced by almost 20 times. This 94% means 20 times. Actually, 95% means 20 times, because this means that your query was running, for example, for 100 seconds, and after the migration from Loki to VictoriaLogs, your query started running in 6 seconds. 100 minus 24, you get 6 seconds. So the actual reduction of response times are around 20 times. And VictoriaLogs allowed saving storage costs by 40% and allowed reducing memory and CPU usage by in half. You can read this real story from this user. So let's return to the log collection, cost-effective logs collection to in Kubernetes. You can install this VictoriaLogs manually, but I recommend you using Helm charts for collecting logs. We provide this VictoriaLogs collector Helm chart, which automatically discovers all the logs from all the containers in Kubernetes and collects these logs and sends these logs to centralized VictoriaLogs. And we provide Helm chart for installing a single node version of VictoriaLogs in Kubernetes and for installing a cluster version of VictoriaLogs. What about traces? I think that traces are overhyped on a large scale. Traces are good for a small scale when you run some system, microservice-based system with tens or hundreds of different microservices, and you need to figure out what is going on in your system during the development or during the debugging. In this case, traces are excellent. But if you run a system, production system, which handles thousands of requests per second, then, and if you try enabling traces on this system, I think that I'm sure that that you will switch off this tracing as soon as possible, because the amounts of data this tracing generates will be enormous, and it will consume much more resources, computer resources, compared to the original system which is monitored with these traces. So the traces cannot be cost-effective by definition. That's why I don't recommend you using these traces. But if you still want using traces, we have a solution from VictoriaMetrics, which is named Victoria Traces. It is more cost-effective compared to Grafana Temp and Elasticsearch. As for ClickHouse, it is comparable to ClickHouse. Okay, and what about continuous profiling? It sounds great, but in practice, it has close to zero practical sense. Why? Because profiling is used mostly as a one-time event. For example, if you see that your application works slowly, then it's probably a good time to profile this application, identify bottlenecks in this application, and remove these bottlenecks from the application. And after you optimize your application, after you remove these bottlenecks from your application, then there is zero sense to run this continuous profiling. If your application starts working slower over time, then you run this one-time profiling and perform this optimization, and that's all. That's why I think that continuous profiling is good for marketing, but bad for practice. And that's all.
Hey, so what's the reason for the poor performance of Prometheus? Is it just poor and bad implementation comparing to VictoriaMetrics, or is it something that you sacrifice when switching from Prometheus to Victoria?
Could you repeat the beginning of the question? What's the reason?
I'm wondering why Prometheus is so, cost inefficient. Why it consumes so much memory? Is it like implemented badly? Is Victoria better in that terms, or is there something that you sacrifice, like in terms of functionality, features, or something like that?
I think that the main reason is that the original architecture of Prometheus is different compared to original architecture of VictoriaMetrics, and the original goals of Prometheus there was no this goal of high resource efficiency of Prometheus. There was no such goal. And when I started creating VictoriaMetrics, this was top priority goal, one of the top priority goals. So the next top priority goal was ease of use, but the first top priority goal was high resource efficiency. That's why VictoriaMetrics is better.
If cost efficiency in Victoria is the top one priority, then what has been moved down in terms of priorities? Have you sacrificed anything when implementing? What kind of decisions have you made to make it more efficient?
Yeah, I think that we sacrificed big number of features because we try implementing only the core features which are useful for the majority of users of VictoriaMetrics, and we try rejecting or providing some workarounds for feature requests which are not needed for the majority of user base of VictoriaMetrics. That's the main reason. But when you compare the amounts of features of Prometheus with the amounts of features of VictoriaMetrics, useful features, then the number of useful features in VictoriaMetrics is bigger compared to Prometheus. For example, Prometheus doesn't have this cardinality explorer, and this is only one of the many useful features which improves lives of DevOps who need to manage the system or need to understand what's going on.
All right. Another question, if I may, about the cardinality explorer. How does it work in the VM cluster setup when you have multiple VM selects, VM inserts? Is it are the stats combined across instances, or do you have separate stats for each instance of VM select, for example?
In cluster mode, VictoriaMetrics collects, will select component, collects all these stats which is collected individually per each storage node, and then combines the stats. And that's why the stats for cluster mode, the stats can be not so accurate. We document this, but the stats still serves the original purpose. The stats allows you identifying labels, metrics which might be dropped, and you can save resource usage on VictoriaMetrics.
All right, thanks a lot.
Great talk. I was wondering why you so quickly gave up on fighting off ClickHouse, which is, by my understanding, just general purpose database. And I think your whole talk was about the product that is tailored for observability.
Yeah, good question. Thanks for notifying me about this ClickHouse question. ClickHouse is a very good database, general purpose analytical database. It is very fast, resource efficient, and you can store metrics and logs and traces and whatever in ClickHouse and get very fast responses from ClickHouse over big amounts of data. But the problem is that ClickHouse is general purpose analytical database. This means that you need to manually optimize ClickHouse for each particular use case. When you store metrics for it, you need to think of the database structure, of table scheme, of indexes, and so on. And if you define this database structure in an efficient way, then the ClickHouse might be very, very inefficient and very, very slow. So you need an expert knowledge for creating fast and efficient observability system on top of ClickHouse compared to VictoriaLogs and VictoriaMetrics, because VictoriaLogs and VictoriaMetrics are optimized for storing metrics and for storing logs, and they work efficiently out of the box without any configuration.
Yeah, for example, for logs, I'm having problems imagining how columnar storage, ClickHouse has a columnar storage as an analytical database, how it would store logs. I guess it would be good for aggregating the results, but still.
Probably you mean this structured logs with different sets of fields per each log. There are multiple different schemes for ClickHouse, and as I know, recently ClickHouse added this new JSON type, the field type for storing these structured logs. But this JSON type is also needs additional configuration, and this additional configuration is non-trivial. If you improperly configure these options for this JSON type, then you will get awful performance, and nothing will work as expected.
Because I guess it's not a database for rows. Row-oriented data.
No. That's not the case. ClickHouse is a column-oriented database, and that's why it is high performant. Actually, it can it can aggregate data with billions of rows per second, like VictoriaMetrics and VictoriaLogs do. And actually, VictoriaMetrics and VictoriaLogs internally use this column-oriented storage too, and this storage and scheme is inspired actually by ClickHouse.
Okay, just for your information, we've run a bit over. We can still pick up maybe one question, and then you can move it outside. Is there still someone who'd like? Yeah.
What do you think about parametric retention time? So you don't configure the retention time for the whole metrics, but you can configure it per metric sets.
VictoriaMetrics actually supports this ability to configure retention per some filters, metric filters, but this ability is available only in enterprise version, as I remember, not in open source. Let me check, I didn't remember this. But we are not going to add support for this case for VictoriaLogs. Why? Because it contradicts the storage scheme used by VictoriaLogs, and it doesn't work well with this storage scheme. And we could implement this functionality, but it will be not satisfied satisfied by the majority of users who want this feature, because it will increase resource usage, it needs additional disk I/O, it needs additional CPU, and it slows down everything. And for logs, there is a better solution. You can store logs with different retention requirements on different storage nodes, and then query all the storage nodes via a single select node. And cluster version of VictoriaLogs is very flexible. You can combine single node version of VictoriaLogs with a cluster version of select components. You can query single node version of VictoriaLogs, and we can query storage nodes in the same way. And you can it is very flexible, and it always solving this problem with different retentions per different sets of logs.
Okay. That was a lengthy Q&A session. If you have more questions for Alexander, please catch him outside. There's still 15 minutes of break. Big applause for Alexander. Thank you very much.